All right. What we can get away with. There we go. Okay, so red light is used in Young's experiment with slits separated by 0.00001. See, look how small that is. That's 1.2 times 10 to the negative 4 meters. Okay, that should work. The screen is located 2.7 meters from the slits. Find the distance on the screen between the central bright and the third bright fringe. Oh my gosh, we've got to find this distance y. Let me set that up and let's just work through that. I will show you how this is a good example of Young's double slit experiment. It's probably one of the harder ones we would do. And so let's just take a look at it. So let me get Young's double slit here. And I'll walk you through it. And then this will be enough. This will be enough to keep you busy. And then on Tuesday, we'll finish this chapter real quick. Just add a little bit of extra stuff. And it's really cool. The Rayleigh criterion and all that and type things. And you'll be ready. You guys showed me that you can, if I kind of tell you where to focus, you guys do a pretty darn good job. So here we go. So we got D is equal to 1.2 times 10 to the negative 4 meters. And the distance from the screen, L, is equal to 2.75 meters. All right, so keep that image in your head. All right, and we've got these two angles. Now we got to find these angles. Now, how are we going to find, what's this? Well, what do we have? We've got the tangent of the angle between here and here. Okay, it's just going to come out to be a tangent of the angle problem. Sorry, I was kind of talking to myself there going, are you sure you're going to be able to do this? Because the answer is going to be right there. So let's take a leak. Take a leak. Take a peek. Maybe I've had too much coffee. All right. That was terrible. I shouldn't have said that. So here we go. I've already forgotten what the question is asking. Oh, M3. Well, these two are the same. So we got to find M equals 3. Okay, what the distance is up there for M equals 3. Piece of cake. We can do that. So at M equals 3. Okay? All right, so here we go. So let's just look at, now this is constructive. It's a bright fringe, so it's constructive interference. So we're going to look at this equation here. We've got d sine theta equals m times 1/2, and we're going to put a 3 in here. So we've got d sine theta is equal to m times lambda. D was equal to 1.20 times 10 to the negative 4 meters times the sine of the angle, which we don't know, which is equal to 3 times, what did they say, 600 nanometers? Was that what we're talking about here? 606, red light, 664 nanometers. All right, cool. So we got this. And lambda is equal to 6.64 times 10 to the negative 7 meters. All right. Okay. So here we go. And this makes sense to me. Now look, we're going to get a really small angle here. This sine thing, I'm saying I'm going to do this to you. I'm going to do this to you. There's a thing in calculus that we teach, and you might have learned it in a higher trig class or something, and it's the small angle formula. Look at this angle that we're going to be looking at. We're going to be looking at the sine of theta is equal to 3 times 6.64 times 10 to the negative 7 meters divided by 1.2 times 10 to the negative 4 meters. This thing is almost 1,000 times bigger than this one. That's going to be a really small freaking number. Even when this is going to be 10 to the negative 6 when we get done multiplying, it's still going to be in the 100s. It's still going to be in the 100s. Let me show you something. Let me show you something here on the calculator. And this is what I'd have you do in class. I'm going to change my calculator over to radians. Look. Oh! Man, sorry about that. So look, let's take 0.001, okay? Now, let's take the sine of 0.001. I'll be darned. It darn near equals 0.001. 9.9 times 10 to the negative 4 is 0.999999 is 0.00999. 3 zeros in all those nines. Look at the tangent. It's 0.001. So the sine is almost equal to the tangent, which is almost actually equal to the number. Okay? When you're dealing with the 1,000s. So we don't even have to convert it we don't even have to use the tangent function. We can just use the sine function. And we can use the inverse sine function to figure out which we... we can use the inverse function. So let's just use theta is equal to... So I'm going to say this. I'm going to say that the tangent of theta is equal to this. Is equal to this over this. Okay. Which is also equal to delta y over L. Delta y over... I'm spitballing here because I'm going to say these two guys are really close to being the same. So if I take 3 times L times this divided by that, I'm going to get what delta y is. The way they might do it is they might convert this. They might find what this is the sine of, then do the tangent of it, and then set it up that way. Whatever. I'm saying I can do it this way. And I'm going to get real close to their answer. 3 times, and this will be the last thing we do. It better be. 3 times this divided by, times 2.75. I'm just going to go ahead and divide it by 1.2 second e to the negative 4 is equal to 0.0166. This may not be small enough. And I'm going to say that that's the same thing as the times 3. 0.0498. I wonder what they got for an answer. It's pretty close. 0.0498. See what they did? They did the inverse. They went ahead and did the inverse sine. Okay, fine. I like the way I did it. Okay? Now the next stuff that we're going to be doing that's coming up on this isn't that hard. We're just kind of looking. We're not going to do thin film. I'll talk about it in class. We're not going to do we'll talk a little bit about diffraction, single slit diffraction, because that's what's going on when you open a door. That's why you can't see around the corner. But the equation's real easy. You've seen this. It's the same thing, but this one points to the dark fringes instead of the bright. And then we'll do resolving power when we come back. All right? And look at some of the homework problems. But you should be good. We're all good. Great. Thank you.